File is a cutting tool used in removing excess material from a workpiece. Files are manufactured in different types and grades to meet the various needs. File grades are determined by the spacing of the teeth. A rough file is used for removing rapidly a larger quantity of metal. It is mostly used for trimming the rough edges of soft metal castings. A bastard file is used in case where there is a heavy reduction of material. A second cut file is used to give a good finish on metals. It is excellent to file hard metals. It is useful for bringing the jobs close to the finishing size. A smooth file is used to remove small quantity of material and to give a good finish. A dead smooth file is used to bring the material to accurate size with a high degree of finish. The types of files used for prepping the workpiece before cutting the square slots are rough file, finishing file. Prick punch or dot punch. Punches are used to make certain dimensional features of the layout permanent. The angle of the prick punch is 30 degrees or 60 degrees. The 30-degree point punch is used for making light punch marks needed to position dividers. The 60-degree punch is used for marking witness marks and called as dot punch. Drilling machine. A drilling machine is a power tool that is used to create cylindrical holes in a workpiece. The tool bit is rotated at high speed and pressed into the workpiece to create a cylindrical hole that passes either partway, blind hole, or all the way through hole, the part. The speed and the feed rate of a drilling machine can be adjusted either manually or automatically. Drilling machines can be mounted directly to a concrete floor, to a work table, or can even be portable. In case of our workpiece, we chain drill holes along the witness marks created by the punch. Chipping is an operation of removing excess metal with the help of a chisel and hammer. The chisel is a hand-cutting tool used by fitters for chipping and cutting off operations. Chisels are made from high carbon steel or chrome vanadium steel. The cross-section of chisel is usually hexagonal or octagonal. The cutting edge is hardened and tempered. A chisel has the following parts, that is, head, body, point or cutting edge. The type of chisel used for separating material after chain drilling operation is a web or a punching chisel. An engineer's hammer is a hand tool used for striking purposes while punching, bending, straightening, chipping, peening, forging, riveting, etc. The major parts of a hammer are a head and a handle. The parts of a hammer head are face. The face is the striking portion. Slight convexity is given to it to avoid digging off the edge into the job. Peen or pane. The peen is the other end of the head. It is used for shaping and forming work like riveting, peening and bending. The peen is of different shapes like the ball peen, cross peen, straight peen. The face and the peen are hardened. A ball peen hammer is used for punching, chiseling, peening, removing bends, and for straightening of sheets. Cheek. The cheek is the middle portion of the hammer head. The weight of the hammer is stamped here. This portion of the hammer head is left soft. Eye hole. An eye hole is meant for fixing the handle. It is shaped to fit the handle rigidly. The wedges fix the handle in the eye hole. The ball peen hammers are used for general work in a workshop. Clearance groove of specified form and dimensions created by removing material at an inner corner of a rotationally symmetric workpiece, and which is necessary for subsequent machining and assembly with mating parts. Types of relief grooves are as follows. Relief groove types E, F, and G are all used for different types of workpieces. Type E is used for pieces with no increased demands on the plane surface but with cylindrical surfaces which may need further processing. Type F is used for pieces with right angle surfaces which may require further machining. While type G is used for pieces which require a small transition of the right angle surfaces with less load. Now let us see job sequence for cutting square slot in workpiece. Check the given raw material for its size. Rough and finish file on surfaces flat and square to overall size of 70 by 70 by 11 millimeters. Maintaining the accuracy of plus or minus 0.04 millimeters. Mark off sizes in part 1 as per job drawing and punch witness marks. Hold part 1 in drilling machine table and drill chain drill holes to remove excess metal as shown. Periphery of the drill should not touch the witness marks. Cut and remove the chain drilled hatched part using web chisel and ball peen hammer. File the chipped portion to size and shape using safe edge file of different grades, maintaining the accuracy of plus or minus 0.04 millimeters, and check the size with vernier caliper. Cut relief grooves using hacksaw at 4 inside corners as shown. Job sequence for square insert to be fitted inside this square slot. File to size 30 by 30 by 11 millimeters, maintaining the accuracy of plus or minus 0.04 millimeters. Check the flatness and squareness with tri-square. Check the size with vernier caliper. Match part 2 into part 1 as shown. Finish filing in part 1 and 2 with flat smooth file and deburr in all the surfaces and corners of the job. Apply a little oil and preserve it for evaluation. In this video, we have learned how to mark a square slot on the workpiece using dot punch and to chain drill the mark without touching the periphery of the witness marks. Use of tools like chisel and hammer to remove excess material from the chain drilled slot. Maintaining the fit accuracy between the square slot and insert and create a seamless mating of the two parts. Thank you for watching. Hello everyone, welcome to this video of Make Inside Square Fit. In this video, we will understand the tools, machine and instruments that are used to maintain the dimensional accuracy to fit a square part in square slot. A file is a cutting tool used in removing excess material from a workpiece. Files are manufactured in different types and grades to meet the various needs. File grades are determined by the spacing of the teeth. A rough file is used for removing rapidly a larger quantity of metal. It is mostly used for trimming the rough edges of soft metal castings. A bastard file is used in case where there is a heavy reduction of material. A second cut file is used to give a good finish on metals. It is excellent to file hard metals. It is useful for bringing the jobs close to the finishing size. A smooth file is used to remove small quantity of material and to give a good finish. A dead smooth file is used to bring the material to accurate size with a high degree of finish. The types of files used for prepping the workpiece before cutting the square slots are rough file, finishing file. Prick punch or dot punch. Punches are used to make certain dimensional features of the layout permanent. The angle of the prick punch is 30 degrees or 60 degrees. The 30-degree point punch is used for making light punch marks needed to position dividers. The 60-degree punch is used for marking witness marks and called as dot punch. Drilling machine. A drilling machine is a power tool that is used to create cylindrical holes in a workpiece. The tool bit is rotated at high speed and pressed into the workpiece to create a cylindrical hole that passes either partway, blind hole, or all the way through hole, the part. The speed and the feed rate of a drilling machine can be adjusted either manually or automatically. Drilling machines can be mounted directly to a concrete floor, to a work table, or can even be portable. In case of our workpiece, we chain drill holes along the witness marks created by the punch. Chipping is an operation of removing excess metal with the help of a chisel and hammer. The chisel is a hand-cutting tool used by fitters for chipping and cutting off operations. Chisels are made from high carbon steel or chrome vanadium steel. The cross-section of chisel is usually hexagonal or octagonal. The cutting edge is hardened and tempered. A chisel has the following parts, that is, head, body, point or cutting edge. The type of chisel used for separating material after chain drilling operation is a web or a punching chisel. An engineer's hammer is a hand tool used for striking purposes while punching, bending, straightening, chipping, peening, forging, riveting, etc. The major parts of a hammer are a head and a handle. The parts of a hammer head are face. The face is the striking portion. Slight convexity is given to it to avoid digging off the edge into the job. Peen or pane. The pane is the other end of the head. It is used for shaping and forming work like riveting, peening and bending. The peen is of different shapes like the ball peen, cross peen, straight peen. The face and the peen are hardened. A ball peen hammer is used for punching, chiseling, peening, removing bends, and for straightening of sheets. Cheek. The cheek is the middle portion of the hammer head. The weight of the hammer is stamped here. This portion of the hammer head is left soft. Eye hole. An eye hole is meant for fixing the handle. It is shaped to fit the handle rigidly. The wedges fix the handle in the eye hole. The ball peen hammers are used for general work in a workshop. Clearance groove of specified form and dimensions created by removing material at an inner corner of a rotationally symmetric workpiece, and which is necessary for subsequent machining and assembly with mating parts. Types of relief grooves are as follows. Relief groove types E, F, and G are all used for different types of workpieces. Type E is used for pieces with no increased demands on the plane surface but with cylindrical surfaces which may need further processing. Type F is used for pieces with right angle surfaces which may require further machining. While type G is used for pieces which require a small transition of the right angle surfaces with less load. Now let us see job sequence for cutting square slot in workpiece. Check the given raw material for its size. Rough and finish file on surfaces flat and square to overall size of 70 by 70 by 11 mm. Maintaining the accuracy of plus or minus 0.04 mm. Mark off sizes in part 1 as per job drawing and punch witness marks. Hold part 1 in drilling machine table and drill chain drill holes to remove excess metal as shown. Periphery of the drill should not touch the witness marks. Cut and remove the chain drilled hatched part using web chisel and ball peen hammer. File the chipped portion to size and shape using safe edge file of different grades, maintaining the accuracy of plus or minus 0.04 mm and check the size with vernier caliper. Cut relief grooves using hacksaw at 4 inside corners as shown. Job sequence for square insert to be fitted inside this square slot. File to size 30 by 30 by 11 mm, maintaining the accuracy of plus or minus 0.04 mm. Check the flatness and squareness with tri-square. Check the size with vernier caliper. Match part 2 into part 1 as shown. Finish filing in part 1 and 2 with flat smooth file and deburr in all the surfaces and corners of the job. Apply a little oil and preserve it for evaluation. In this video, we have learned how to mark a square slot on the workpiece using dot punch and to chain drill the marked slot without touching the periphery of the witness marks. Use of tools like chisel and hammer to remove excess material from the chain drilled slot, maintaining the fit accuracy between the square slot and insert and create a seamless mating of the two parts. Thank you for watching. Hello everyone, welcome to this video of File Fit Combined Open Angular and Sliding Sides. In the previous video, we understood the procedure to make a sliding T-fit with interchangeability. We also learned about the limits, fit and tolerances. In this video, we will learn about angular measurement, geometric tolerances on shape or form, orientation and position used to file and fit combined, open angular and sliding slides. Angular measurement of angles of an object is usually expressed in degrees, minutes and seconds. 1 degree is divided into 60 minutes and 1 minute is into 60 seconds. The tool used to measure angles accurately with precision is the vernier bevel protractor. The vernier bevel protractor is a precision instrument meant for measuring angles to an accuracy of 5 minutes. The following are the parts of a vernier bevel protractor. Stock. This is one of the contacting surfaces during the measurement of an angle. Dial. The dial is an integrated part of the stock. It is circular in shape and the edge is graduated in degrees. Blade. This is the other surface of the instrument that contacts the work during measurement. It is fixed to the dial with the help of the clamping lever. Locking screws. 2 knurled locking screws are provided. One to lock the dial to the disc and the other to lock the blade to the dial. The vernier bevel protractor is used to measure acute angles less than 90 degrees and obtuse angles more than 90 degrees. The tolerance on size is also called as dimensional tolerance. But these tolerances may not be sufficient to manufacture the desired fit perfectly. So, we require additional tolerances called geometrical tolerances as shown in the example. These are of following 3 types: tolerances on shape or form, tolerances on orientation, tolerances on position. The geometrical tolerances is represented in terms of symbol, tolerance value and reference datum. Let us see tolerances on shape or form with the following characteristics. Straightness. It is the characteristic of a line where all the elements of a line are collinear. In general, there could be 2 lines within which all the points lie on a line. Flatness. It is defined as minimum distance between 2 planes within which all the points lie on a surface. A surface where all the points lie along single plane is called as perfectly flat surface. Circularity. It is defined for a cylindrical or conical surfaces as the distance between the surface and its axis. Ideally, all points on a surface at a cross-section should be equidistant from the axis for the cross-section to be perfectly circular. The tolerance on circularity is defined by 2 concentric circles within which a surface can lie. The distance between the 2 concentric circles is called tolerance. Cylindricity. It is defined for a surface of revolution as the distance between the surface and its axis. Ideally, all points on a surface of revolution should be equidistant from the axis for the cross-section to be perfectly cylindrical. The tolerance on cylindricity is defined by 2 concentric cylinders within which a surface can lie. The distance between the 2 concentric cylinders is called tolerance. Profile of line or surface. It is defined for a line or surface of any shape as the distance between 2 lines or surfaces of the same shape as that of the line or surface in question, separated by a distance equal to tolerance. Tolerances on orientation. Parallelism. It is defined for a feature like surface or line with reference to another feature called reference. It defines the distance between two lines or surfaces that are parallel to each other and parallel to the datum surface and encompass the line or surface in question. Perpendicularity. It is defined for a feature like surface or line with reference to another feature called reference. It defines the distance between two lines or surfaces that are parallel to each other and perpendicular to the datum surface and encompass the line or surface in question. Angularity. It defines the distance between two lines or surfaces that are at an angle to the datum surface and encompass the line or surface in question. With respect to position, it defines the perfect exact location of a point, line, or a surface in relation to the other datum. Concentricity. It defines the position of an axis in relation to the other datum axis. It defines a cylinder which coincides with the datum axis and of diameter given by the geometrical tolerance. Run out. It defines the deviation from the desired form and orientation during one full rotation of the part on the datum axis. Let us now learn the procedure to file and fit open angular and sliding sides of mating workpieces. Check the raw material for its size. File part 1 and 2 to overall size of 78 by 48 by 9 mm, maintaining parallelism and perpendicularity. Check the size with vernier caliper. Apply marking media and mark dimension lines on part 1 and 2 as per job drawing. Punch witness marks on part 1 and 2. Hacksaw and remove the excess metal in part 1 and file to size and shape, maintaining accuracy of plus or minus 0.04 mm and angle of 30 minutes. Drill diameter 3 mm relief hole in part B. Chain drill. Chip, remove the excess metal in part B and file to the size and shape. Check the size with vernier caliper and angles with vernier bevel protractor. Finish file on part 1 and 2 and deburr in all corners. Match part 1 and 2 as shown. Apply a little oil and preserve it for evaluation.
In this video, we learned how to take angular measurements and use of vernier bevel protractor, concept of geometric dimensioning and tolerancing GD and T,
How to file fit combined open angular and sliding sides of mating workpieces.
Thank you for watching. Hello everyone.
Welcome to this module of File Internal Angles 30 Minutes Accuracy Open Angular Fit.
In this video, we will learn to read angular measurements using bevel protractor understand parts of a vernier caliper, and to read a vernier caliper as per the required accuracy. We will also understand the procedure to file internal angles with 30-minute accuracy for angular fit.
A vernier bevel protractor is used to take angular measurements. There are two graduations. The main scale division, MSD. For purposes of taking angular measurements, the full circumference of the dial is graduated in degrees. The 360 degrees are equally divided and marked in 4 quadrants, from 0 degree to 90 degrees, 90 degrees to 0 degrees. Every 10th division is marked longer and numbered. Each division represents 1 degree. The graduations on the dial are known as the main scale divisions. The vernier scale division, VSD. On the disc, 23 divisions spacing of the main scale is equally divided into 12 equal parts on the vernier. Each third line is marked longer and numbered as 0, 15, 30, 45, 60. This constitutes the vernier scale. Similar graduations are marked to the left of 0 also. The least count of the vernier bevel protractor. When the 0 of the vernier scale coincides with the 0 of the main scale, the first division of the vernier scale will be very close to the second main scale division. Now, 1 MSD is equal to 1 degrees. 1 VSD is equal to 23 by 12 degrees. Hence, the least count is calculated as least count is equal to 2 MSD minus 1 VSD, which is equal to 2 degrees minus 23 by 12 degrees, which is equal to 24 minus 23 by 12 degrees, which is equal to 1 by 12 degrees, since 1 degree is equal to 60 minutes, which is equal to 1 by 12 degrees into 60, which is equal to 5 minutes. Therefore, least count of vernier bevel protractor is equal to 5 minutes. For reading acute angle setup, first read the number of whole degrees between 0 of the main scale and 0 of the vernier scale. Note the line on the vernier scale that exactly coincides with any one of the main scale divisions and determines its value in minutes. To take the vernier scale reading, multiply the coinciding divisions with the least count. Example, 10 into 5 minutes is equal to 50 minutes. Total up both the readings to get the measurements, which is equal to 41 degrees 50 minutes. If you read the main scale in an anti-clockwise direction, read the vernier scale also in an anti-clockwise direction from 0. The vernier scale reading up is taken on the left side as indicated by the arrow. The reading value is subtracted from 180 degrees to get the obtuse angle value. Reading is 22 degrees 30 minutes. To subtract reading value from 180 degrees, measurement is equal to 180 degrees minus 22 degrees 30 minutes, since 1 degree is equal to 60 minutes, which is equal to 179 degrees 60 minutes minus 22 degrees 30 minutes, which is equal to 157 degrees 30 minutes. Care and maintenance of vernier bevel protractor. Clean the vernier bevel protractor before use. Loosen the locking screw of dial to move the blade according to the angle measurement. While taking a measurement, apply light pressure on vernier bevel protractor. Heavy pressure will force the two scales out of parallel and show the false reading. After using vernier bevel protractor, wipe it clean and apply a thin coating of oil and keep it in safe place. Now let us see the different parts of a vernier caliper. Fixed jaws 1 and 2, Fixed jaws are part of the beam scale. One jaw is used for taking external measurements and the other for taking internal measurements. Movable jaws 3 and 4. Movable jaws are part of the vernier slide. One jaw is used for external measurements and the other for internal measurements. Vernier slide 5. A vernier slide moves over the beam and can be set in any position by means of a spring-loaded thumb lever. Beam 6. The vernier slide and the depth bar attached to it slide over the beam. The graduations on the beam are called the main scale divisions. Depth bar 7. The depth bar is attached to the vernier slide and is used for measurement of depth. Thumb lever 8. The thumb lever is spring-loaded, which helps to set the vernier slide in any position on the beam scale. Vernier scale 9. The vernier scale is the graduation marked on the vernier slide. The divisions of this scale are called vernier divisions. Main scale. The main scale graduations or divisions are marked on the beam. Determining the least count of vernier caliper. 49 main scale divisions are equal to 50 vernier scale divisions. Therefore, 1 VSD is equal to 49 upon 50 millimeters. 1 MSD is equal to 1 millimeters. Least count is equal to 1 MSD minus 1 VSD, which is equal to 1 millimeter minus 49 by 50 millimeter, which is equal to 50 minus 49 by 50 millimeters, which is equal to 1 by 50 millimeters, which is equal to 0.02 millimeters. Therefore, least count of vernier caliper is equal to 0.02 millimeters. 1 inch of the main scale is divided into 10 major divisions, and each of these is further divided into 4 equal parts. The value of each division is 1 by 10 into 1 by 4, which is equal to 1 by 40 inches, which is equal to 0.025 inches. One main scale division is divided into 25 divisions on vernier scale. Therefore, least count is equal to 1 by 40 inches divided by 25, which is equal to 1 by 40 inches into 1 by 25, which is equal to 1 by 1000 inches, which is equal to 0.001 inches. Therefore, least count of vernier caliper is equal to 0.001 inches. To file internal angles with 30-minute accuracy for angular fit. Check the raw material size. File part 1 and 2 to overall size 74 by 47 by 9 millimeters, maintaining flat and squareness. Apply marking media on the surface and mark dimension lines on part 1 and 2 as per job drawing. Punch witness marks on part 1 and 2. Drill diameter 3 mm relief holes in part 1 and 2. Hacksaw and remove the excess metal in part 1 and file the cut portion to size and shape, maintaining the accuracy plus or minus 0.04 millimeters and angles 30 minutes. Chain drill, chip, hacksaw and remove the excess metal in part 2 and file to size and shape. Check the size with vernier caliper and angles with vernier bevel protractor. Match part 1 and 2. Apply a little oil and preserve it for evaluation.
In this video, we learnt to measure angles accurately by understanding the graduations and least count of the vernier bevel protractor, different parts of vernier caliper and its least count to measure linear dimensions accurately, procedure of filing internal angles to a 30-minute accuracy and matching sliding parts to create an angular fit. Thank you for watching. Hello everyone. Welcome to this video of Make and Assemble Sliding Flat Plane Surfaces. In this video, we will gain an understanding of taps, reamers, and their parts. Additionally, we will learn practical skills to make and assemble sliding flat plane surfaces.
Hand taps are used for internal threading of components. They are made from high carbon steel or high-speed steel, hardened and ground. Threads are cut on the surface and are accurately finished. To form the cutting edges, the flutes are cut across the thread. For holding and turning the taps while cutting threads, the ends of the shanks are squared. The end of threaded body of the taps are chamfered, taper-led, for assisting, aligning and starting of the thread. The size of the taps, the type of the thread, and pitch are usually marked. Generally, circles are marked to indicate the types of taps. One circle, first tap or taper tap, is to start the thread. Two circles, second tap or intermediate tap. Three circles, plug tap or bottoming tap or finishing tap is used to finish the threads of a blind hole to the correct depth. These taps are identical in all features except in the taper lead angle. Tap wrenches are used to align and drive the hand taps correctly into the hole to be threaded. Tap wrenches are of different types. Double-ended adjustable tap wrench or bar type tap wrench. This is the most commonly used type of tap wrench. It is available in various sizes. These tap wrenches are more suitable for large diameter taps and can be used in open places where there is no obstruction to turn the tap. It is important to select the correct size of wrench. T-handle tap wrench. These are small adjustable chucks with two jaws and a handle to turn the wrench. This tap wrench is useful to work in restricted places and is turned with one hand only. This wrench is not available for holding large diameter taps. Solid type tap wrench. These wrenches are not adjustable. They can take only certain sizes of taps. This eliminates the use of wrong length of the tap wrenches and thus prevents damage to the taps. What is a reamer? A reamer is a multi-point cutting tool used for enlarging by finishing previously drilled holes to accurate sizes. Reamers are classified as hand reamers. Reaming by using hand reamers is done manually, for which great skill is needed. Hand reamers have straight shanks with square at the end for holding with tap wrenches. Machine reamers are fitted on spindles of machine tools and rotated for reaming. They are provided with Morse taper shanks for holding on machine spindles. Parts of a hand reamer. Axis, the longitudinal center line of the reamer. Body, the portion of the reamer extending from the entering end of the reamer to the commencement of the shank. Recess, the portion of the body which is reduced in diameter below the cutting edges, pilot or guide diameters. Shank, the portion of the reamer which is held and driven. It can be parallel or taper. Circular land, the cylindrically ground surface adjacent to the cutting edge on the leading edge of the land. Bevel lead, the bevel lead cutting portion at the entering end of the reamer cutting its way into the hole. It is not provided with a circular land. Taper lead, the tapered cutting portion at the entering end to facilitate cutting and finishing of the hole. Bevel lead angle, the angle formed by the cutting edges of the bevel lead and the reamer axis. Taper lead angle, the angle formed by the cutting edges of the taper and the reamer axis. Terms relating to cutting geometry. Flutes, the grooves in the body of the reamer to provide cutting edges, to permit the removal of chips and to allow the cutting fluid to reach the cutting edges. Heel, The edge formed by the intersection of the surface left by the provision of a secondary clearance and the flute. Cutting edge. The edge formed by the intersection of the face and the circular land or the surface left by the provision of primary clearance. Face. The portion of the flute surface adjacent to the cutting edge on which the chip impinges as it is cut from the work. Rake angles. The angles in a diametral plane formed by the face and a radial line from the cutting edge. Clearance angle. The angles formed by the primary or secondary clearances and the tangent to the periphery of the reamer at the cutting edge. Helix angle. The angle between the edge and the reamer axis. Moving on to make and assemble sliding flat plane surfaces. File job for part 1, 2, 3 and 4 to size and shape as per drawing. Apply marking media on part 2 and 3. And mark to locate the dowel pin holes, countersink screw holes as per drawing. Assemble and clamp part 1, 2, 3 and 4 together in drilling machine table with parallel clamps. Fix diameter 3.8 mm drill in drilling machine spindle. Through drill chuck and drill through hole. Fix diameter 4 mm hand reamer in tap wrench and ream the drilled hole to fix diameter 4 mm dowel pin without disturbing the assembly setting. Clean the reamed hole and insert diameter 4 mm dowel pin. Similarly, drill holes for other 3 dowel pin holes one by one and ream the drilled holes one by one and fix the dowel pins without disturbing the assembly. Fix diameter 4.2 mm drill in drilling machine spindle through drill chuck and drill holes for tap drill holes for fixing countersink screws in assembly without disturbing the setting. Separate the assembly parts 1, 2, 3 and 4 and chamfer the tapping holes both ends in part 1 using countersink tool. Hold part 1 in bench-wise. Drill free hole diameter 5.5 for countersink screw on part 2 and 3 and countersink the hole to seat countersunk head screw. Cut internal thread using M5 hand tap and tap wrench. Clean the thread without burrs. Assemble part 1, 2, 3 and 4 as per job drawing along with dowel pins and countersink screws. Fit and slide part 4 in the assembly. Disassemble all the parts from assembly. Finish file on the surface of part 1, 2, 3 and 4 and remove burrs in the corners of the job. Reassemble all the parts together as per job drawing. Apply thin film of oil and preserve it for evaluation.
In this video, we learnt about taps and reamers, practical skills to make and assemble sliding, flat, plane surfaces. Thank you for watching. Hello everyone.
Welcome to this module of Check for Blue Match of Bearing Surfaces, both flat and curved surfaces by Whitworth method.
In this video, we will understand need for scraping surface, Whitworth principle, and checking for blue match of bearing surfaces, both flat and curved surfaces by Whitworth method.
How does one obtain a flat surface? If three plates are compared with one another in alternate pairs, they will only mate perfectly in all positions when they are absolutely flat. File and ensure that all the three plates are finished to size and square. Stamp the plates X, Y and Z with a letter punch. Apply a very thin uniform coating of Prussian blue on the faces of plates X and Y, which are to be scrapped. Keep both the pieces together and rub the plates back and forth against each other. Observe the high spots on the plates X and Y, remove by scraping with knitted cotton cloth. Rub with an oil stone gently to remove the burrs and again clean with knitted cotton cloth. Repeat the same procedure till both the faces are mating with good bearing surfaces. Apply a very thin uniform coating or Prussian blue on the face of the plate Z, which is to be scrapped. Keep the faces of the plates X and Z together and rub the plates back and forth against each other. Observe the high spots on the plate Z and remove by scraping. Repeat the same procedure till both the faces of the plates X and Z are mating with good. Repeat the procedure till the faces of plates Y and Z are mating with good bearing surfaces. Now, one cycle of operation is completed. Plate X will mate with plates Y and Z, but Y and Z will not mate. All the three plates mate only when all the three are flat. So, repeat the cycle a number of times till interchangeable, flat, good bearing surfaces are achieved. For scraping flat surfaces, the following two scrapers are used. Flat scrapers with rectangular blades. Used for scraping large flat surfaces. The working edge is not thicker than 3 mm. Hook scrapers with rectangular blades. Used for scraping the center portion of large flat surface where it is not convenient to use flat scraper. A half-round scraper is the most suitable scraper for scraping curved surfaces. For scraping curved surfaces, the handle is held by hand in such a way as to facilitate the movement of the scraper in the required direction. Pressure is exerted with the other hand on the shank for cutting. Rough scraping will need excessive pressure with longer strokes. For fine scraping, pressure is reduced and the stroke length also becomes shorter. Cutting action takes place both on forward and return strokes. During the forward movement, one cutting edge acts and on the return stroke, the other cutting edge acts. After each pass, change the direction of cutting. This ensures a uniform surface. Use a master bar to check the correctness of the surface being scraped. Apply a thin coating of Prussian blue on the master bar to locate the high spots. For scraping on flat surface, check the raw material for its size. File metal to size 96 by 96 by 10 mm, maintaining flatness and squareness. Check the size with vernier caliper. Clean the surface plate with soft cloth. Apply Prussian blue evenly on the surface plate. Place the job on surface plate and move slightly forward and backward. Take the job from surface plate and notice the blue spotted marks on the flat surface. Hold the job in benchwise. Scrap and remove the high spots on the flat surface of the job using flat scraper. Wipe off the scraped surface with soft cloth to remove burrs. Again, place the scraped surface on Prussian blue applied surface and move forward and backward and notice the high spot marks. Repeat the scraping process until the Prussian blue spotted marks spread over the entire surface of the job. Wipe off the scraped surface with soft cloth. Apply thin coat of oil and preserve it for evaluation. Now, checking the blue match on flat surface. After scraping the flat surface, clean the surface plate with soft cloth. Apply Prussian blue evenly on the surface plate. Place the job on the surface plate. Move slightly forward and backward and notice the blue match spread over the entire flat surface. For scraping on curved surface, check the raw material for its size. File metal to size 90 by 48 by 18 mm, maintaining flatness and squareness. Check the size with vernier caliper. Apply marking media, mark and punch. Chain drill holes remove excess material. Cut and remove the hatched portion of chain drilled holes, excess metal using web chisel and ball peen hammer. File curved surface with half round file and check the curved profile with template. Hold the round test bar diameter 60 mm in bench vise along with vise clamps. Apply thin coat of Prussian blue on the one end of cylindrical surface of test bar. Place the curved surface of the job on Prussian blue applied test bar and rotate back and forth. Notice the blue spotted marks on curved surface. Hold the job in bench vise. Scrap and remove the high spots on the curved profile surface using half round scraper. Wipe off the scraped surface with soft cloth to remove burrs. Again, apply Prussian blue on the test bar and place the curved scrapped surface on test bar and rotate back and forth. Repeat the scrapping process until the Prussian blue spotted marks spread over the entire curved surface of the job. Wipe off the scraped surface with soft cloth. Apply thin coat of oil and preserve it for evaluation. To check the blue match on curved surface. After scraping the curved surface, clean the cylindrical test bar with soft cloth. Hold the test bar in bench vise along with vise clamp. Apply Prussian blue evenly on the curvature of the test bar. Place the curved surface of the job on test bar and rotate slightly on back and forth. Notice the blue match spread over the entire curved surface.
In this video, we learnt to originate flat scraped surfaces by the three-plate method or Whitworth principle. to check for blue match of both flat and curved bearing surfaces. Thank you for watching. Hello everyone. Welcome to this video of
File and fit combined radius and angular surface, accuracy plus or minus 0.5 millimeters, angular and radius fit.
In this video, we will learn about outside micrometer, scale graduation, its parts and function. Also, we will see the procedure to file and fit the radial and angular surfaces of two mating workpieces.
A micrometer is a precision instrument used to measure a job, generally within an accuracy of 0.01 millimeters. Micrometers used to take the outside measurements are known as outside micrometers. The parts of a micrometer are listed here. Frame. The frame is made of drop-forged steel or malleable cast iron. All other parts of the micrometer are attached to this. Barrel or sleeve. The barrel or sleeve is fixed to the frame. The datum line and graduations are marked on this. Thimble. On the beveled surface of the thimble also, the graduation is marked. The spindle is attached to this. Spindle. One end of the spindle is the measuring face. The other end is threaded and passes through a nut. The threaded mechanism allows for the forward and backward movement of the spindle. Anvil. The anvil is one of the measuring faces which is fitted on the micrometer frame. It is made of alloy steel and finished to a perfectly flat surface. Spindle lock nut. The spindle lock nut is used to lock the spindle at a desired position. Ratchet stop. The ratchet stop ensures a uniform pressure between the measuring surfaces. Working principle of micrometer. The micrometer works on the principle of screw and nut, where circular motion is converted into linear motion. The longitudinal movement of the spindle during one rotation is equal to the pitch of the screw. The movement of the spindle to the distance of the pitch or its fractions can be accurately measured on the barrel and thimble. Graduations on micrometer. In metric micrometers, the pitch of the spindle thread is 0.5 millimeters. Thereby, in one rotation of the thimble, the spindle advances by 0.5 millimeters. On the barrel, a 25 millimeter long datum line is marked. This line is further graduated to millimeters and half millimeters. That is 1 mm and 0.5 mm. The graduations are numbered as 0, 5, 10, 15, 20 and 25 millimeters. The circumference of the bevel edge of the thimble is graduated into 50 divisions and marked 0 to 5 to 10 to 15 up to 45 to 50 in a clockwise direction. The distance moved by the spindle during one rotation of the thimble is 0.5 millimeters. Movement of one division of the thimble is equal to 0.5 into 1 by 50, which is equal to 0.01 millimeters. Accuracy or least count of a metric outside micrometer is 0.01 millimeter. Micrometer with graduations in inches. On micrometers with graduations in the inch system, the datum line on the barrel of the micrometer is graduated to 1 inch. This 1 inch is divided into 10 equal parts and each of this is further subdivided into 4 equal parts. The value of each subdivision is equal to 1 by 40 inches or 0.025. The thimble had 25 equal divisions marked on the circumference. The least count is equal to 1 by 40 inches into 1 by 25, which is equal to 1 by 1000 inches, which is equal to 0.001 minute. When the spindle of the micrometer advances by one division on the thimble, the actual value of the linear movement is equal to 0.001 inches. Now let us move on to know the functions of its various parts. Ratchet stop. This is a device fitted on micrometers to ensure uniform pressure between the measuring face of the micrometer while measuring. The ratchet stop will slip beyond certain pressure, thus preventing further advancement of the spindle when excessive pressure is used. This is mounted on the thimble of the micrometer and it connects with the spindle when assembled. A special spanner is provided along with the micrometer for fixing and removing the ratchet stop. Thimble. The thimble has a hollow taper to match with the taper nose fitted on the spindle. Spindle. One end of the spindle forms the measuring face. The other end of the spindle is threaded. The tapered nose is fitted on it. The taper nose is very accurately finished for axial alignment, and it also permits positioning of the thimble in any required place during the adjustment of zero error. The spindle passes through a split internal thread which forms part of the barrel. The outer portion of this split internal thread has tapered external threads. A taper-threaded nut is fitted on this. Tightening and loosening of this nut enables the split internal thread to close or open. This permits the wear adjustment in the mating threads. A special spanner is provided for this purpose. The locking device provided on the spindle is to arrest the movement of the spindle after taking the measurement. Procedure to file and fit combined radius and angular surface. Part A. Check the raw material size using steel rule. File and finish to overall size of 74 by 60 by 9 mm, maintaining parallelism, perpendicularity and to the accuracy of plus or minus 0.04 mm. Check the size with vernier caliper. Apply marking media, mark as per drawing and punch witness marks. Drill relief holes of diameter 3 mm. Hacksaw and remove the hatched portion of excess metal in one side. Part B. File and finish to overall size of 74 by 50 by 9 mm, maintaining parallelism and perpendicularity and to the accuracy of plus or minus 0.04 mm. Check the size with vernier caliper. Apply marking media, mark as per drawing and punch witness marks. File to size maintaining accuracy of plus or minus 0.04 mm for linear dimension and 30 minutes accuracy for angular dimension. Check the size with vernier caliper and angle with vernier bevel protractor. Similarly, cut and remove excess metal in other side and file to size and shape. Then cut and remove the excess metal in curvature side and file curved profile to size and shape. Check the curved profile with template or radius gauge. Drill relief holes of diameter 3 mm and drill chain drill holes to remove excess metal. Hacksaw, chip and remove the hatched portion of excess metal and file the chipped portion to size and shape. Hacksaw and remove the hatched portion of excess metal on curved surface. File the curved portion to size and shape. Check the curved profile with template. Match Part A and B. Finish file in Part A, B and remove the burrs in all the corners. Apply a little oil and preserve it for evaluation.
In this video, we learnt functional parts of micrometer and to read the scale of micrometer. Procedure to create interchangeable machine parts to fit radial and angular surfaces in an assembly. Thank you for watching.
Locate accurate holes and make accurate hole for stud fit.
Hello everyone. Today we'll be looking into the process of fitter practical sessions to locate accurate holes and make accurate holes for stud fit.
Topics: how to file surfaces flat and square. Mention tap drill size for tapping hole and drill the hole. Cut N10 internal thread using tap and wrench. Fit stud in the threaded hole. Tools and equipment required. Identify the tools and equipment used in fitter section. Record the names of tools, do's and don'ts of each tool. Record the names of the industries where the fitters are employed. Common tools: steel rule, tri-square, scriber, flat file, dot punch, needle file, bench vise, hacksaw, tapping wrench, drill bit, vertical drill, vernier caliper, hammer, N10 tap, pitch gauge. Safety precautions in fitting. Demonstration activities, shop talk with safety. Safety attitude development of the trainee by educating them to use personal protective equipment. Identify personal protective devices. Interpret the different types of personal protective devices. Eye protection, safety glasses, foot protection, safety shoes, dust and fumes, respirators, hands safety, gloves, head safety, helmet, hearing protection, earplugs, clothing, safety jacket, prevent from falling, safety harness. File metal to size 48 x 48 x 9 mm, maintaining flatness and squareness. Locate accurate holes and make accurate hole for stud fit. Objectives: file surfaces flat and square. Determine tap drill size for tapping hole and drill the hole. Check the raw material for its size. Mark the dimensions of the material using scale and scriber. Cut the required length using a hacksaw. File metal to size 48 x 48 x 9 mm, maintaining flatness and squareness. Check the size with vernier caliper. Apply chalk on the surface of the material to mark the center. Mark drill hole at the center of the job as per drawing. Place the component on the surface and using a dot punch mark the center for drilling. Hold job in benchwise. Mention the drill size for M10 tap. Locate accurate holes and make accurate hole for stud fit. Cut M10 internal thread using tap and wrench. Fit stud in the threaded hole. Place the component on the surface and using a dot punch mark the center for drilling. Fix 6 mm drill bit and drill pilot hole. Fix 8.5 mm drill bit and drill through hole for tapping. Hold the job in benchwise. Cut M10 internal thread using hand tap and tap wrench. Clean the thread to remove the burrs. Check the thread with screw pitch gauge. Fit stud in the threaded hole. Recap. Tools and equipment required. Safety precautions in fitting.
Now you have learned to file surface flat and square. Determine tap drill size for tapping hole and drill the hole. Cut M10 internal thread using tap and wrench. Fit stud in the thread hole. Hope you had a clear understanding on this technical process. Thank you.
Hello everyone, welcome to this video of
Fasten mechanical components or sub-assemblies together using screws, bolts, and collars using hand tools.
In this video, we will learn how to fasten mechanical components or sub-assemblies together using screws, bolts, and collars with the help of hand tools.
Drilling a through and blind hole for part 1 of the assembly. Check the raw material size. File and finish the metal to size 60 by 60 by 19 mm, maintaining parallelism and perpendicularity. Check the flatness and squareness with dry square and size with vernier caliper. Apply marking media and mark centers for drilling holes using vernier height gauge as per drawing. Punch on centers for drilling holes using center punch 90 degrees. Hold the job in drilling machine table. Make center drill in drill holes centers. Fix diameter 6 mm drill in drilling machine spindle through drill chuck and drill pilot holes for both through and blind holes. Fix diameter 8.5 mm drill and drill through hole as per drawing. Fix diameter 10.5 mm drill and drill blind hole to the required depth of 14 mm. File and deburr in all the surfaces of the job. Cut internal thread in through hole. Fix the job in benchwise. Fix M10 first tap in tap wrench and cut internal thread in through hole. Similarly, fix M10 second tap and third tap in tap wrench one by one and cut the internal thread to form full thread. Repeat the above process to cut internal thread in other drilled through hole. Cut internal thread in blind hole. Remove metal chips, if any, from the blind hole by turning it upside down and slightly tapping it on a wooden surface. Fix the M12 first tap in tap wrench. Screw a matching nut on the first tap to the required distance of 14 mm to act as a depth stop. Cut internal thread in blind hole to the required depth of 14 mm. Remove the metal chips, if any, from the threaded blind hole. Similarly, fix M12 second tap and third tap in tap wrench one by one and cut the thread to form full thread. Clean the threaded hole and ensure no burrs. Repeat the above process to cut internal thread in another drilled blind hole. Use cutting fluid while cutting the thread. Check the threaded hole using the M10 and M12 matching bolts by screwing. To prepare stud. Check the raw material size. File the round rod ends to flatness and squareness, maintaining size diameter 10 mm by 70 mm length. Turn the round rod to diameter 9.9 mm blank size to cut external thread as per drawing. File chamfer of 2 mm by 45 degrees at both ends of the round rod. Apply marking media on cylindrical surface of the job and mark the required length and punch witness marks to cut external thread as per drawing. Hold the cylindrical rod in benchwise to 90 degrees with aluminium vise clamps and check the 90 degrees with tri-square. Set M10 circular split die in die stock. Place the split die on the cylindrical round rod one end and cut external thread by rotating in clockwise and anti-clockwise direction to cut external thread. Apply pressure on the die stock evenly and turn in a clockwise direction to advance the die in stud blank and reverse the die for a short distance to break the chips. Following the above processes, cut the external thread up to the required length as per drawing. Clean the thread and check with suitable screw pitch gauge and matching nut. If the nut is not fitted with the external thread, increase the depth of cut gradually by adjusting the split die stock, outer screws and deepen the cut of thread to correct pitch of thread and check with matching nut and screw pitch gauge. Similarly, repeat the thread cutting process in other end of cylindrical round rod to the required length and check with suitable screw pitch gauge and match with suitable nut. Clean the thread and ensure no burrs. Apply little oil and preserve it for evaluation. To prepare bolt. Check the raw material for its size. Turn hexagon rod ends to flatness and squareness 9 mm by 40 mm length in lathe. Apply marking media and mark dimensions to prepare hexagonal head bolt blank as per job drawing. Punch witness marks using dot punch 60 degrees. Cut and remove excess metal by sawing. Turn to diameter 9.9 mm by 18 mm length to cut external thread. File chamfer of 2 mm by 45 degrees on screw end of rod. Hold the hexagonal head bolt in benchwise to 90 degrees along with aluminium vise clamps. Set M10 split die in the die stock. Place the split die on the hexagonal head bolt round blank end with die stock and turn in clockwise direction and anti-clockwise direction to cut external thread. Check the die to 90 degrees to the hexagonal head bolt blank while cutting external thread. Apply pressure on the die stock evenly and cut external thread as shown in job drawing. Check the thread with screw pitch gauge and matching nut. Clean the thread, apply little oil and preserve it for evaluation. Moving on to prepare the collar and assembling the 3 parts. Check the raw material size. File flatness and squareness. Mark in collar as per job drawing and punch the hole center and the outer circumference of collar. Drill the center of hole diameter 10.5 mm and chamfer sink the drilled hole both sides. Hold the job in benchwise and file the circumference of collar to diameter 22 mm and thickness 14 mm. The size with vernier caliper. Clean the parts 1, 2 and 3. Assemble the parts 1 and 2 using hexagonal bolt and tighten the bolt using suitable double-ended spanner or ring spanner. Mark the tap drill hole center on middle of the collar as shown in job drawing. Set the assembly in drilling machine table using suitable clamping device. Make drill hole collar diameter 5.2 mm for M6 tap and drill up to opening of internal diameter ID 10.5 mm in hexagonal bolt. Separate the parts 1, 2 and 3. Fix countersink tool in drilling machine and chamfer the diameter 5.2 mm drilled hole. Hold the collar in benchwise. Cut M6 internal thread using hand tap and tap wrench. Reassemble the parts 1, 2 and 3 and tighten the hexagon bolt using suitable double-ended spanner or ring spanner. Screw the round head slotted screw in collar as shown in job drawing and tighten it using suitable screwdriver and complete the sub-assemblies. Apply thin coat of oil and preserve it for evaluation.
In this video, we have learned to drill a through and blind hole, procedure to form internal threads with taps to standard size, to prepare fasteners like stud and bolt, assembling the mechanical components using hand tools like double-ended spanner or ring spanner. Thank you for watching. Hello everyone, welcome to this video of
Make sliding fits assembly with parallel and angular mating surface.
In this video, we will gain an understanding of screw threads, the different types and their measurement. Additionally, we will learn practical skills to assemble sliding fits with parallel and angular mating surfaces.
Thread is a ridge of uniform cross-section which follows the path of a helix around the cylinder or cone either externally or internally. Helix is a type of curve generated by a point which is moving at a uniform speed around the cylinder or cone and at the same time moves at a uniform speed parallel to the axis. Parts of screw thread are Crest, the top surface joining the two sides of a thread. Root, the bottom surface joining the two sides of adjacent threads. Flank, the surface joining the crest and the root. Thread angle, the included angle between the flanks of adjacent threads. Depth, the perpendicular distance between the roots and crest of the thread. Major diameter. In the case of external threads, it is the diameter of the blank on which the threads are cut, and in the case of internal threads, it is the largest diameter after the threads is cut that are known as the major diameter. This is the diameter by which the sizes of screws are stated. For external threads, the minor diameter is the smallest diameter after cutting the full thread. In the case of internal threads, it is the diameter of the hole drilled for forming the thread, which is the minor diameter. Pitch diameter, effective diameter. The diameter of the thread at which the thread thickness is equal to 1/2 of the pitch. Pitch. It is the distance from a point on one thread to a corresponding point on the adjacent thread measured parallel to the axis. Lead. Lead is the distance of a threaded component moves along the matching component during one complete revolution. For a single start thread, the lead is equal to the pitch. Helix angle. The angle of inclination of the thread to the imaginary perpendicular line. Hand. The direction in which the thread is turned to advance. A right-hand thread is turned clockwise to advance, while a left-hand thread is turned anti-clockwise. The different types of threads are: square thread. In this thread, the flanks are perpendicular to the axis of the thread. Square threads are used for transmitting motion or power. For example, screw jack, vice handles, cross slide, compound slide, and activating screwed shafts. Trapezoidal threads. These threads have a profile which is neither square nor V thread form and have a form of trapezoid. The different forms of trapezoidal threads are: Acme thread is a modification of the square thread and has an included angle of 30 degrees. Acme threads are used in lathe lead screws. Buttress thread. In buttress thread, one flank is perpendicular to the axis of the thread and the other flank is at 45 degrees. These threads are used in power press, carpentry vices, gun breeches, ratchets, etc. Worm thread. Similar to Acme thread in shape, but the depth of thread is more than that of Acme thread. Knuckle thread. The shape of the knuckle thread is not trapezoidal, but it has a rounded shape. It is used for valve spindles, railway carriage couplings, and hose connections. Unified V thread. For both the metric and inch series, ISO has developed this thread. Its angle is 60 degrees. Screw threads are used as fasteners to hold together and dismantle components when needed, to transmit motion on machines from one unit to another, to make accurate measurements, to apply pressure, to make adjustments. The screw thread micrometer. This micrometer is used to measure the effective diameter of the screw threads. This dimension is important because the area of the thread flanks in the vicinity of the pitch line, where the greatest transmission of force occurs between mating threads. This is very similar to the ordinary micrometer in construction, but has facilities to change the anvils. The anvils are replaceable and are changed according to the profile and pitch of the different systems of threads. Moving on to make sliding fit assembly with parallel and angular mating surface. Check the raw material for its size. File the materials for part 1, 2, 3 and 4 to overall sizes, maintaining the accuracy of plus or minus 0.04 millimeters. Apply marking media on part 2, 3 and 4 and mark linear dimensional lines with vernier height gauge and angular lines with vernier bevel protector. Punch witness marks on part 2, 3 and 4. Punch on drill hole marks for dowel pins and countersink screws assembly using center punch. Cut and remove the excess metal from part 2, 3 and 4 and file to size and shape as per job drawing, and check the size with vernier caliper and angles with vernier bevel protractor. Assemble and clamp part 1, 2 and 3 together on a drilling machine table with parallel clamps. Fix diameter 3.8 mm drill in drilling machine spindle through drill chuck and drill through holes for dowel pin assembly. Fix diameter 4 mm hand reamer with tap wrench and ream the drilled hole to fix diameter 4 mm dowel pins without disturbing the assembly setting. Clean the reamed hole with soft cloth and insert diameter 4 mm dowel pin. Similarly, drill holes for other dowel pins one by one and ream drilled holes to fix diameter 4 mm 3 dowel pins one by one without disturbing the assembly setting. Determine tap drill size for M4 internal thread. Fix diameter 3.3 mm drill in drilling machine spindle through drill chuck and drill 2 holes as shown in job drawing. Separate the assembly part 1, 2, 3 and 4. Fix countersink tool in drilling machine and chamfer in both ends of drilled holes to cut internal thread in part 1. Hold the part 1 in bench vise and cut internal thread using M4 tap and tap wrench. Fix countersink tool and countersink the drilled holes in part 2 and 3 to seat the countersink head screws and drill a clearance hole for M4 countersink screws. Finish file on part 1, 2, 3, 4 and remove burrs in all corners of the job and assemble the parts all together using dowel pins, countersink screws. Apply a thin coat of oil and preserve it for evaluation.
In this video, we have learned the screw threads, their types and measurement, practical skills to assemble sliding fit with parallel and angular mating surfaces. Thank you for watching.
Today I will be discussing on CPgrams, which is Centralized Public Grievance Redress and Monitoring System developed by NIC for Department of Administrative Reform and Public Grievances. It is an online platform available